Okay, the first question says, researchers wondered whether the number of firefighters sent in response to a 911 call indicating a structure was on fire was related to the resulting cost of damage resulting from such fire. The table to the right contains the number of firefighters assigned to 12 randomly selected 911 calls reporting a structure on fire and the resulting cost of the damage resulting from the fire. Part A says, use your calculator to draw a scattergram treating the number of firefighters as the explanatory variable and the cost of the fire damage as the response variable. Okay, so first thing we have to do is go to our calculators for this one. So let's go to our calculator, hit clear, we're going to go stat, edit, hit enter. We want to erase that list, so we can highlight the L1, hit clear, enter. And then I want to erase list 2, so select L2 with your arrows, then hit clear and enter. Next, we want to input all the values of the explanatory variable, which is going to be the horizontal axis values, otherwise known as x. So we're going to put in 14, 7. Next, we're going to go over to L2, and for L2, we're going to put in all the values of the cost of damage. So starting with $133.2 thousand, then 103.9. Okay, next we're going to select y equals. Notice that there's an equation there. That might cause a problem when I try and graph this. So I'm going to clear to get rid of it. Then I'm going to hit second shift stat plot. Okay, this is a nice overview of the plots. The second and third plot are off. That's good. I do want one of them on, so select that guy. Select it on, then use your arrows. I do want the very first graph. That's already been selected, so I'm good with that. Hit enter. And then I want to tell it where the x and y coordinates are going to be. List 1 and list 2 is where they are, so this is good. Next, I'm going to hit zoom, and then I want to scroll down to the 9th option. Zoom stat. Enter, and there they are. There's my scattergram. I can use this as a guide now, so that when I go over here and try and plot these values, it'll be something that looks similar to that. Keep in mind that I've already placed the horizontal and vertical scale, so that should make it easy to plot these. So we don't really actually need the calculator, but that's just a nice way of verifying it. Okay, so next I'm going to plot each one of these points on my grid. The first one being 14, 133.2. So the scale's already on here. 4, 6, 8, 10, 12, 14 is here. And I want to go up to 133.2. That should be, I don't know, a little bit past this line, like maybe around there. Okay, it doesn't have to be super perfect, just guideline, rough estimate. The next one is at 7, 103.9. So here's 6. 7 is going to be somewhere in the middle, and we're going to go up to 103.9. So just a little bit past 100, maybe around there, and so on and so forth. Note that I did make a mistake here, and I pushed 30, which is off the scale here. If you didn't graph that point, that's fine. Otherwise, if you chose to put a point somewhere out here at, say, 30 and 20 something, somewhere around here, that would have been fine as well. Okay, part B says use your calculator to compute the linear correlation coefficient value of R. Let's go to our calculator. We already put all our values onto list 1 and list 2. List 1 and list 2. So all we have to do is hit stat, calculate, and then the fourth option down here says linear regression ax plus b. Select that. Tell it where the x and y coordinates are. So list 1, second shift list 2, close parentheses, enter, and there it is. So here's the value of R, 0.7958. That's all we have to do. Now if you did this and you didn't get the value of R, that's because your calculator doesn't have the diagnostics on function. So to turn it on, to activate it, you got to hit second shift catalog down here above the 0 and scroll all the way down until you see diagnostics. Diagnostics on, select that, hit enter, it says done, and now if you do the whole process again, now you'll get the desired response of 0.7958. Okay, 7958 then goes here. Okay, moving on. Is there enough evidence to indicate a linear relation? Explain and use the critical value for correlation coefficients to justify your answer. Okay, so a table was given to you with values that indicate the cutoff point, the minimum number required in order to get a linear relationship. So the first thing we have to do is count how many values we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 values. So now if we go over to our table, which was given to you, say it's something like this, then we see that for n equals to 12, the value is 0.76, 0.576. Okay, so now that means that because our value is greater than that, then we do have enough evidence. Okay, so there are several good answers here. So let's say okay, something to that effect would be good. Notice it's the absolute value of R, meaning that if we had gotten a negative answer up here, then we strip away the negative and then just look at its positive, compare that to the correlation coefficient value, and if it's greater than that, then we'd have a negative linear correlation. But in this case, we have a positive one. Okay, so that takes care of part C. Part D says, use your calculator to find the mean standard deviation for both the number of firefighters and the amount of fire damage caused. Okay, so this is a nice, simple calculator question. We can go back to our calculator, and we already have all the values we needed into list 1 and list 2. So all we have to do is go to Stat, Calculate, and let's do a 2-variable statistics test. And we're going to do it on list 1, comma, list 2. So this will just do both of them at the same time, all the results we want for list 1 and list 2. Otherwise, you can do a 1-variable stats on list 1, get the responses that you need, write them down, and then go back and do the same thing for list 2, a 1-variable stats for list 2. Okay, so from here we can see that the mean of x is 11.9167. Now we have to choose between the two standard deviations. In this particular case, we clearly have a sample of 911 calls. This is not all 911 calls ever made. So we have to use S sub x. If we have a situation where we know the data is a population, it's not a sample, but it's all of them, then we'd use sigma. But in this case, clearly it's got to be that S sub x equals to 8.1626. Plus, if you notice, I was nice enough to give you the notation of S sub x instead of sigma, so you don't make that mistake. Now if you scroll down, we will also get the values of y bar, 84.9917, and again the value of S sub y and sigma sub y. And again, I was nice enough to give you S sub y in your test, so you can tell which one I'm looking for. Okay, so all you have to do is type each one of these in here, and we're home free. So you got to type in okay, there we are. Moving on. Okay, now part E says, find the least squares regression line by using the formula in the last page. No calculator, show your work, then graph the line in the line on the same graph from step A. Oops. Okay, so graph the line back on the grid we got on top on the first page here. Okay, so if you looked in the back of your book, there was equations for these if you didn't have them memorized. So we know that the least squares regression line will be a linear equation that follows the form y hat equals to b sub 1 x plus b sub naught. This is where b sub 1 is equal to r times s sub y divided by s sub x. Okay, and so we got all these values in page 1, so we can just type them in here. B sub 1 is going to be equal to the value of r, which we found to be 0.7958. And we're going to multiply that by a giant fraction, where the numerator is s sub y, or 49.3959, and the denominator is s sub x, or 8.1626. So we can use our calculator and figure out that that is approximately equal to 4.8158. Okay, so now that we have b sub 1, we can go over and find the value of b sub naught, where we are told that b sub naught is equal to y bar minus b sub 1 times x bar. And again, we have all these values up from page 1. Y sub bar is 84.9917 minus b sub 1, which just figured out to be 4.8158, and we're to multiply that times the mean of x bar, which is 11.9167. Okay, so then we use our calculator to calculate that, and we get a value of approximately 27.6033. Now we can bring everything together and write the equation of y hat to be equal to 4.8158x plus 27.6033. So we have an equation where we input the number of firefighters that we send to a 911 call, and this equation will model the resulting damage in thousands of dollars, which is y hat. We can also use function notation to describe this same thing as f of x equals to 4.8158x plus 27.6033. Either one would be fine. Okay, so now let's not forget that we were asked to graph this equation onto the grid on page 1. So we can go to our calculator first. Let's go to our calculator and type it in there. 2, and we can graph that. So there, it looks something like that. And then we can go back to our own grid on page 1. So let's go back to our own page grid, like something like that. And we can do kind of a rough guesstimation of that onto there. Okay, so something to the effect of that. It doesn't have to be perfect. Something along those lines would have been fine. Okay, moving on to the next part of this question, part F. It says, according to our regression line, how much fire damage should be expected when 22 firefighters are assigned a 911 call reporting a structure fire? Okay, so we have this function where we input the number of firefighters and the output is the amount of damage. In this case, we're going to solve this equation with letting x equal to 22. So we start off with let x equal 22, and we're going to have f of 22 equals to 4.8158 times 22 plus 27.6032, and then we use our calculator to figure out what that is, and we get something pretty close to 133.5508, I think. Something like that. Okay, so if 22 firefighters are assigned to this 911 call, we would expect, according to our model, that there would be about $133,551 worth of damage. Okay, moving on. If a structure fire is known to have caused $45,000 in damage, approximate the number of firefighters who responded to the 911 call. Okay, so we're going to use the exact same formula that we've been using, except this time the value of 45 is the result from some unknown value of x. So then we're going to set up our equation this way. 45 equals to 4.8158 x plus 27.6032, and now we do some algebra skills here to solve for x. So we're going to subtract minus 27.6032 from both sides of the equation, minus 27.032, and then we're going to divide, so we're going to end up with x equals to 45 minus 27.6032 divided by 4.8158, and then we can use our calculator to find the value of that, and so we'll end up with 3.6124. Okay, so we can round this to the nearest firefighter and be 4. So this is stating that if there was a structure damage with $45,000 in damage, then we estimate that about 4 firefighters were assigned to the fire. Okay, moving on to the last part of this question. If government officials intend to use the regression equation from step E to reduce the cost of fire damage to 0, how many firefighters should be assigned to respond to 911 calls reporting a structure fire to bring the expected structure fire damage down to 0? Okay, well, if we just apply our equation, we're going to do the same thing that we did for G, but instead of putting a 45, now we're going to set it equal to 0. So this would be 0 equals to 4.8158x plus 27.6032. And now again, we use our awesome algebra magic to solve for x. We subtract 27.6032 from both sides of the equal sign and divide. And we'll get that x is going to be equal to negative 27.6032 divided by 4.8158. And we should get a value of about negative 5.7318. Okay, which makes no sense. It makes no sense from the standpoint of the equation, but ultimately it shouldn't make any sense going back to the original premise of this question, that the government intends to use the regression equation to reduce the cost of damage. And that's because we've established that there is correlation between these two variables and not causation. That's very important. So just because these two variables, the number of firefighters and the resulting damage, are correlated, they both go up at the same time, or as one variable goes up, the other variable goes up as well, or as one variable goes down, the other variable also goes down. Just because there is a positive linear relationship between the two does not mean that one causes the other. Okay, so there's several good answers to this one. Something, for example, of the form... Okay, so here's one possible response. The number of firefighters and the resulting amount of fire damage are correlated. Those two variables are correlated, but we have not established causality. It is silly to think that you can affect the amount of damage caused by changing the number of firefighters assigned to the structure. One doesn't cause the other. Okay, so very big and important distinction between two variables that are correlated and two variables that have established causality, which we have not in this case. Okay, so that's the end of number 1. Okay, question 2 states, in the game of roulette, a player can place a $10 bet on the number 13 and have a 1 in 39 probability of winning if the middle ball lands on 13. The player wins $300. Otherwise, the casino takes the player's $10. Compute the expected value of the game from the player's point of view by filling out the following table. Okay, so let's fill this guy out. First, we have to establish the two possibilities whenever you play one game. So one option could be that a player puts down $10. That's $10 there. And he either wins or if he loses. Now, let's keep track of the signs. From the player's point of view, putting down $10 and potentially losing it is a negative. On the other hand, winning is a positive, so the winnings would come over here. Now, a lot of people think that the answer is 300 here, but that's not the case, because you put down $10 and then you win, or they give you back 300, but you've already given them 10, so really the winnings are $290. Okay? Now the probability of winning is only 1 in 39, so this is 1 divided by 39. And the probability of losing then is going to have to be 38 divided by 39. So we can convert those into decimals if we like. Now to find the mean of this probability distribution table, we're going to have to follow our formula, which we've stated right up here. We multiply x times p of x, and then we got to sum down. So this is going to be equal to negative 380 divided by 39, which equals to roughly negative 9.7436. And then over here we end up with a fraction of 290 divided by 39, which is then going to be equal to roughly 7.4359. So all of that sums up to negative 2.3077. Okay. Now, if you bet 1,000 games each time placing a $10 bet on the number 13, how much do you expect to win or lose? Okay, so if we multiply 10,000 times negative 2.3077, we end up with negative 23,077. Negative $23,072. So that's our answer. Okay, so there's several good answers to this, but here's one possible solution. Because the expected value of the game is negative 2.3077, This means that in the long run, we can expect to lose $2 at $2.3077 per game. So if we play 10,000 games, sometimes we win, sometimes we lose, but over the long run, we can expect to lose a lot more than we win. We can expect to lose $23,077. Question 3 now. State whether the following are discrete probability distributions. Circle yes or no, and if not, state why. Okay, looking at each one of these distributions, if it is in fact a discrete probability distribution, it must satisfy the two conditions, which are that each probability must be between 0 and 1, no negative probabilities, no probabilities greater than 1, and also that the sum of the probabilities must be equal to 1. So if we look at number 1, everything looks good. So yes, it is a discrete. Some people might be concerned about this, but that's okay. You're allowed to have a 0 as a probability. That means that 2 just can't happen, and that's fine. Looking at this one, everything looks good. Again, some people might be concerned about this part here, that they're all zeros there, but that's okay. You're allowed to have all zeros as long as the two conditions are satisfied. Each probability is between 0 and 1, and the sum is equal to 1. So yeah, that's 1. Okay, over here, if we notice, all the probabilities are between 0 and 1, but if we add them up, they do add up to something greater than 1, so this is not a proper discrete probability distribution. And under reasons why, I would say you can write something to the effect of sum of p of x is greater than 1, or you can just say Riemann sum of p of x was greater than or equal to 1. Any one of those two would be fine, and that would indicate that it failed that rule. The sum was greater than 1. You can also add them up and say that they sum up to 1.5, I believe. So sum of p of x equal to 1.5, which is greater than 1. So that's why it fails. All right, over here, no problems there. The sum does add up to 1, and so this is a proper probability distribution, so we're okay. Over here, we have a problem right there, right? We are not allowed to have a negative probability, so this is not a probability distribution. And for the reason, you can put that the probability of x equaling 2 is equal to negative 0.15, and negative probabilities are not allowed. So, but all p-values have to be between 0 and 1. 0 less than p of x less than 1, less than or equal to 1. Okay, so all probabilities must be between 0 and 1, and that one is not compliant, so that's why it's not a proper distribution. Finally, the last one, everything looks good here again. Some people might be concerned about this, that there's a negative there, but that's okay. We're allowed to have negative answers. It's the probabilities themselves that can't be negative. So this is a proper probability distribution. Okay, that's it for 3. Okay, question number 4 states that there are 35 million residents of California. Of the 35 million residents, it is known that 65% have smoked marijuana at some point. What is the probability that among 12 randomly selected Californians, exactly 2 have smoked marijuana? Use the binomial probability equation, not the calculator function, to express your answer. Use your calculator to find the answer, and then finally interpret your results by writing a full sentence. And then, for example, if 1,000 randomly selected groups of size blank are selected, we would expect blank, 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 blank. Okay, so back to the beginnings here. Is this a binomial situation? Well, I hope so, because the question, in fact, is telling you to use the binomial probability equation. But if that was not on there, if this just said solve it, how would we know? Well, we have to make sure that this question satisfies the 4 conditions of a probability, a binomial probability situation. So the first one is that there is a fixed number of trials. In this case, there are 12 trials, so that's true. And then for each trial, there are two mutually exclusive outcomes. So for each person that we select, we are going to ask whether or not they have smoked marijuana at some point. So this is a yes or no question. And so, yes, there are two mutually exclusive outcomes. The third one is that the probabilities must be independent. If we randomly pick one person, their response cannot affect the response of another randomly selected person. Yes, that's good here. And finally, that the probabilities are constant from trial to trial. And yes, that's also going to be true here. Notice this is one of those cases where technically this is conditional probability and it wouldn't meet those standards of a binomial. But because we have such a large pool, 35 million residents, and from there we are only taking a sample of 12, then we get to ignore those technicalities and think of this as a binomial situation. Okay, so now if we look at our equation, then we'll see that the probability that we randomly select 12 Californians and exactly 2 have smoked marijuana is equal to the following. Okay, so it is the probability that x equals to 2, the random variable equals to 2, is equal to combinations of 12 choose 2. That's because there are 12 trials, 12 people are being selected, and we are looking at the case where exactly 2 of them have smoked marijuana at some point. Then we multiply times the probability of success, where here success is that we find an individual who answers in the positive, in the affirmative. And that's being given to us as 65%, so it's 0.65 to the power of 2 because there are 2 of them, times 0.35 to the power of 10, because if there are 2 people that said yes, then there must be 10 people that said no in our sample of 12. So this is the equation, and now we just use our calculator to find the result, and we should get something very similar to 0.0007692. Okay, so what does this mean? It means it's got a very low chance of occurring. There's different ways of putting this, but the way I like to think about it is that if we randomly select groups of size 12, then how many of those groups are going to have exactly 2 that have smoked marijuana? So there's different ways to answer this question. Here's one example. Okay, if 1,000 randomly selected groups of size 12 are selected, okay, so you have 1,000 separate groups, each one of size 12, we would expect about 0.7692 groups, or approximately 1 group, to have exactly 2 people who have smoked marijuana. Now, I just randomly picked the 1,000. In retrospect, it might have been a little bit more reasonable to randomly pick a different group instead of 1,000, maybe 10,000, and then I think this definition makes a lot more sense. So, for example, okay, so if 10,000 randomly selected groups of size 12 are selected, okay, you got that? So 10,000 groups, each group has 12 people in it. We would expect that about 7.62 groups, or about approximately 8 out of the 10,000, are groups that have exactly 2 people who have smoked marijuana. Okay, all other 9,992 groups have other responses. Maybe some of those groups only have 1 person in the group. Some of those groups have 7 people in the group. So there's only, we estimate that there should only be 8 groups in those 10,000 that have exactly 2 people who have smoked marijuana. Okay, so hopefully that makes sense. Okay, moving on to part B of the same question. Notice that I've provided you with several calculator functions just to refresh your memory on which functions might be useful in this section. And also I've broken down each question into steps 1, 2, 3, just to make sure that you give me the parts that I'm looking for. though in retrospect perhaps this was a little heavy-handed and might have confused people. On the second attempt for this test, I will not have steps 1, 2, 3 broken down. I will just expect you to write them down for full credit. Okay, but let's proceed. B. What is the probability that among 18 randomly selected Californians, exactly 5 have smoked marijuana? Okay, so the probability statement would be this. Okay, so the probability that x equals to exactly 5 equals to binomial PDF of 18, comma, 0.65, comma, 5. Okay, so now let's go to our calculator and figure out what that is. Okay, so second shift distribution, go down to binomial PDF. And it is a total of 18, comma, 0.65 is the probability of success, comma, 5 equals, enter, and there it is, 001175, 001176. Okay, so the probability is 0.001176. Now, a little sentence. I gave you an example before, so there are several good answers, but this is what I like best. Okay, if 1,000 groups of size 18 are randomly selected, we would expect that about 1.2 of those groups, approximately 1 of those groups, would have exactly 5 people who answered yes, they have smoked marijuana at some point. So the other 999 groups of 18 each would have other answers. Perhaps some groups have 5 in the 18 who have smoked marijuana, others have 7, others have 13, but we would expect that only one of them has 5 people who have smoked, exactly 5 people that have smoked marijuana. Moving on to part C. What is the probability that among 15 randomly selected Californians, at most 9 have smoked marijuana? Okay, so because this is an at most, it means that we include the values that are smaller than 9 in including 9. So if we had the probability distribution table for the random variable x, it would look something like this. So in this case, we want to get up to and including 9. So we want all of these probabilities here. Everything up to and including 9. These guys is what we want. And so to get all of those probabilities, we use the calculator function of binomial CDF. Okay, so this was not part of the answer. I was just trying to explain it to you. So the answer would come over here as the probability that x (9). Okay, probability that x is less than or equal to 9 is equal to binomial CDF 15, 0.65, 9. And now we can go to our calculator and punch that in, see what we get. So distributions, scroll down to binomial CDF. And it's going to be 15, 0.65, 9, close parentheses, enter, and we get 4357 approximately. So the answer, the probability answer is. And then as far as an answer, very similar to the one above. Okay, If 1,000 randomly selected groups of size 15 are selected, we would expect that about 436 of these groups would contain 9 or less Californians who have smoked marijuana at some point. Okay, moving on. What is the probability that among 23 randomly selected Californians, at least 18 have smoked marijuana? Okay, so again, if we had a probability distribution table on the random variable x, we would see something of the sort. Okay, so the random variable x could take on the value 0, and then 2, 1, and 2, and 3, and so on and so forth. And way down here, we'd have the values 23, and 22, and 21, and 20, and 19, and 18, and 17, and so on and so forth. Okay, so this wanted at least 18, so that means that we have to find the probabilities of 18 or larger. At least 18 must be 18 or larger. So these are the ones we want. Now, we don't have a calculator function that will help us find the values from 18 forward, but we do have a function that helps us find the values from 0 up through and including the value of 17. So we're going to find those, and then we're going to use the complement rule to find the values that we actually want. Okay, so that's not part of the solution. The solution should look like this. Okay, so probability that x is greater than or equal to 18 is equal to 1 minus binomial CDF of 23, 0.65, 17. And if we look at our calculator and get an answer for that, we'll get the following. Clear. Let's see, we want 1 minus binomial CDF of 23, 0.65, 17, close parentheses, enter. So we get 0.1309. So this is going to be the probability that x is greater than or equal to 18. Okay, so if 1,000 randomly selected groups of size 23 are selected, we would expect that about 131 of those groups would contain at least 18, meaning 18 or more, Californians who have smoked marijuana at some point. Okay, moving on to E. What is the probability that among 135 randomly selected Californians between 73 and 94 have smoked marijuana? Okay, so again, let's look at the probability distribution. If we looked at the probability distribution of the random variable x, it would look something like this. We'd have, of course, x there, and then all the way down here, we'd have probability of x over there. Okay, so the random variable x could take on the value 0, 1, and so on and so forth. And then way down here, we'd have 135 as another option. And then somewhere in the middle, we'd have these values. There's a 73 somewhere over here. And whoa, down here, and then there's like a 94 somewhere over there. And we want the values that are between these. Now, it didn't really quite make it clear whether or not to include the 73 and the 94. It just says between them. Well, by default, if they don't say to include them, we shouldn't include them. So we really want the values starting at 74. Really want the values starting at 74 all the way up to and including the value of 93. So these are the ones we want, from 74 to 93. Okay, so how can we find these? Well, we can find all the values from 0 up through and including 93. That would be the values starting there and going all the way up to 93 by binomial CDF. And then, because we don't want these numbers here, we're going to subtract off the unwanted ones. Okay, so that's the game plan. So the solution is this. Okay, so probability that x is strictly between 73 and 94 is equal to the probability that x is greater than or equal to 74 but less than or equal to 93. Okay, so first we're going to get the values from 0 through and including 93 with binomial CDF of 135, 0.65, 93 minus binomial CDF of 135, 0.65, 73. So let's go to our calculator and figure out what that is. Second shift distribution. Binomial CDF. 135, 0.65, 93, close parentheses, minus so 0.8448. Okay, so the probability that x is between 73 and 94 is 0.8448. And again, for a sentence, okay, if 1,000 randomly selected groups of size 35 are size 135 are selected, we would expect that about 845 groups would contain between 73 and 94 Californians who have smoked marijuana at some point. Okay, moving on to the last one in this question. What is the probability that among 135 randomly selected Californians, either strictly less than 29 or strictly more than 78 have smoked marijuana? Okay, so let's just jump to the answer there. Okay, notice that, so we have probability that x is strictly less than 29 means that we want to include the values from 0 all the way up to and including 28, and that's what this part of the statement will give me, binomial CDF of 135, 0.65, 28, from 0 to 28, that'll be part of these people. Now the other ones are strictly greater than 78, so I want 79 or larger, 79 larger. So the complement would be to include from 0 to 78 and do 1 minus that to get me the complement, and that would include 79 or larger. So we'd have this, 1 minus binomial CDF of 135, 0.65, 78. Okay, so now let's go to our calculator and figure out the result of that. binomial CDF 135, comma 0.65, comma 28, close parentheses, plus 1 minus binomial CDF comma 0.65, comma 78. I get 0.9511. Okay, so if 1,000 randomly selected groups of size 135 are selected, we would expect that about 951 groups would contain either strictly less than 29 or strictly more than 78 Californians who have smoked marijuana at some point. Okay, so the other 49 groups out of the 1,000, 49 of them would have other results that don't lie in those regions. There would be 49 groups of size 135 each, where the number of Californians that have smoked marijuana at some point would lie somewhere between 29 and 78. So as you can see, the vast majority of results lie in the tails, either less than 29, meaning from 0 all the way up to and including 28, or strictly more than 78, which would be from 79 forward. Okay, that's it for this question. Okay, moving on to question 5 now. Assume that the random variable x is normally distributed with a mean of mu equals to 20 and a standard deviation of 3.4. Compute the probability that x is greater than or equal to 18.9 but less than or equal to 22.1. Okay, so first of all, we got to go over to our distribution and label it as normal. It's not standard normal, though, because the mean is given to us as 20, and the standard deviation is... Okay, and now they want to know what's the probability that one randomly selected value of x is between 18.9, so let's say that that's like here, and 22.1. Let's say that that's over here. Okay, so we want all the values that are in here. There. I want all the values that are in there. Okay, so to find this answer, we're going to use the calculator function normal CDF. So the answer should be okay. So there's our calculator function. Let's use our calculator now to figure out what that is. Normal CDF of 18.9, comma 22.1, comma 20, comma 3.4. And we get 0.3584. Okay, number 6. It says find the z-score that corresponds to the given area under the standard normal curve. Be sure to write the appropriate calculator function. Okay, well, a little redundant here that I labeled it as the z-score as well as the standard normal curve. So, and also over here on the graph, if you notice, it's got the letter z on there. So all those should be a clue that this is the standard normal distribution. So we should label it. Okay, and so mu automatically has got to be equal to 0 because it's the standard normal distribution, and sigma is automatically 1. This random variable here is the random variable z, as we've identified there. Okay, so we want to find the z value that traps the lowest 0.26%, which is going to be a calculator function called invnorm. So let's type in that calculator function. It is going to be invnorm. Now the first thing it wants is the area to the left, so we're going to type in 0.26, comma 0, comma 1, which is the mean and standard deviation. So that is all we need right there. Okay, so let's use our calculator to find the answer. Distributions, invnorm, 0.26, comma 0, comma 1, close parentheses, enter, and I get a negative 0.6433. Going back over here. Answer is answer is negative 0.6433. Okay, so that value belongs over here. This guy right in there is the value that traps the lowest 26% of the data. So this should go right in there. Let's put it right in here. Squeeze it right in there. That z value is negative 0.6433. Okay, moving on. Okay, number 7. The distribution to the right is normal with a mean of 13 and a standard deviation of 2.5. Find the value of A such that the area under the curve between 10.8 and A is 49.5. Note that the shaded region is not symmetric about the center of the normal distribution. Okay, so we got to study this picture here and try and come up with a game plan. There's a couple of good ways to do this, but I think the most direct approach is going to be to find the area of this section over here. That's what we want to find. And then when we find that area, we'll add it to 49.5. That'll give us the entire area from there to there. And then we can find the value of A using inverse norm that way. Okay, so let's find this area here. That'll be the following. That'll be the probability Okay, so the probability that x is less than or equal to 10.8 is equal to normal CDF of negative infinity, put a bunch of 9s there, up through and including 10.8, comma 13, comma 2.5. If we use our calculator to find that, we get the following. $18.94. Okay, so then we come back over here. Alright, so now that we found this area over here, we got to add these two areas together, and that'll give us the whole area to the left of A. So we'll end up with okay, so now finally to find the value of A, we're going to take advantage of the inverse norm function. Okay, so A equals to inv norm of the area to the left, which is going to be 68.44%, 0.6844, comma 13, comma 2.5. Okay, so now let's use our calculator. Distributions in norm 0.6844, comma 13, comma 2.5, close parentheses. So about a 14.2. Okay, so we have the probability that x is less than or equal to 10.8 was normal CDF of negative 99999 up, comma 10.8, comma 13, comma 2.5. And that gave us a result of 1894. That means that this value right in here is the area of 1894. Let's put that on there. So this area is 1894. Now if I add these two areas together, they give me a total area of 6844. So the whole area to the left of A is 68.44%. Now we take advantage of the inverse norm function. A equals inverse norm of 0.6844, comma 13, comma 2.5, and we get a value of A of 14.2. Okay, so now let's move on to the next question. Find the z-score that separates the middle 86% of the distribution from the area in the tails in the standard normal distribution. Okay, so they've already started by letting us know that this is a standard normal distribution, so we got to label it. Let's go over here and label this as standard normal. Okay. Because it's standard normal, that means that the random variable is z, and the mean value has got to be a 0, and sigma is equal to 1. And now they're asking for the two values, find the z-scores, the two values, the middle 86%. So there's going to be some value here, which we'll call z sub 1, and there's going to be some other z value over here, which we'll call z sub 2. And those are the ones I'm looking for. So I want the values, the trap, the middle, say approximately there to approximately there, that area right in there, and I want that area to be 86%. So the middle 86%. If we examine this graph, we see that the two tails must add up to 14%. Which means that each one of these tails must be 7%. So, in order to find the value of z, we can employ the z inverse function. So let's go over here. Okay, so let's use our calculator to find these results. Okay, I get negative 1.4758, 4758. So there's negative 1.4758. And then if we go back to our calculator, distribution, inverse norm, 0.93, comma 0, comma 1, we get positive 1.4758, and that's because it's symmetric. It's centered at 0, so we can take advantage of some of these principles to have some shortcuts. So it makes sense that it would have been positive 1.4758. Okay, so those are the results that are right in here. Let's put them there. This number is the one that goes right in here from negative, let's put it underneath it, negative 1.4758. And this value is the one that goes there. So between negative 1.4758 and positive 1.758, those are the two z values that trap the middle 86% of the standard normal distribution function. Okay, moving on. Okay, number 9. SAT scores are normally distributed with a population standard deviation of 135. Cal Poly San Luis Obispo is a very selective institution that only accepts students who score 1,572 or higher on their SAT test, ranking them in the top 5% of all SAT scores. Find the population mean of the normal distribution that represents all SAT scores. Okay, so we have to study our normal distribution given. So we are told that we have a score that separates the top 5% of 1574. So the picture should look something like this. And so this little section over here is 5% of the distribution. And I know that this score right here that separates the top 5% is the score of 1572. Okay, so in this problem we are not given the values of mu. That's what we're trying to find out. Mu is unknown. And we do know sigma. Sigma is given to us as 135. Okay, so we could take advantage of the formula here for z-scores, because we can easily find how many standard deviations away from the mean you're supposed to go in order to trap the top 5%. So let's find the value of the z-score that does that. So we're going to go over and look at the standard normal distribution, which is given here. This is z's. This is the standard normal distribution. We want the z value that traps the top 5%. That's going to be exactly z sub 0.05. And that's going to be equal to an inverse function, inverse norm, equals inv norm of, now remember the calculator function wants the area to the left, so it's 0.95 to find the value that traps the top 5%, comma 0, comma 1, because we are talking about the standard normal distribution at this point. Okay, so that should do it. Now let's go to our calculator and figure out what that is. So distribution inverse norm of 0.95, comma 0, comma 1, close parentheses, enter. We get 1.6448, so that's the value we're going to use here. Okay, so that's what that equals, 1.6448. Okay, so now if we take a look at this formula right in here, we know the z value now. We know the value of one x value that traps the top 5%, and we know sigma, so we can just use this little formula to find the value of mu, which is what we were looking for. So the formula would be 1.6448 is equal to 1572 minus mu, that's what we're trying to find out, divided by 135. Okay, so now we can do a little bit of algebra magic here and solve for mu. We need to multiply both sides by 135, and then we need to add mu to this side and then subtract that difference over here. So if we do all that, we'll end up with mu is equal to Okay, number 10. When I go to pay for my items at Costco, the lines are always way too long. I always look for the line that has the smallest number of people, but still, I usually have to wait a long time. As a project for my statistics class, I sent my students to walk into a randomly selected Costco at a randomly selected day and time and record the number of customers in the shortest line, meaning that a result of 0 means that in that visit to a Costco, there was at least one line with no customers in it, and a result of 7 means that in that visit to a Costco, the line that contained the least number of people waiting to pay contained 7 customers. The table to the right contains the results. Okay, so let's look at that table. Notice that X is the number of people waiting in line, and they range from 0 through 8. And then that we have frequency, the number of results that came up with those particular values. Okay, so the first thing we have to do is construct a discrete probability distribution of the variable x, the number of customers waiting in the shortest line. Then use your calculator to construct a probability histogram. Be sure to label the horizontal and vertical axis and then write the height of each rectangle at the top of it. Okay, so let's go to our calculator and input all this information. We're going to want to make maybe this one list 1 and list 2 on our calculator. So, that, edit, clear. Okay, so I inputted all the values of list 1 on. Okay. List 1 contains all the values of x, the number of customers waiting in line, ranges from 0 through 8, and list 2 contains all the values of the frequency. So the first thing I want to do is add up the frequencies, figure out how many total results we're talking about. The fastest and best way to do that is to do a one variable statistic on list 2. Second shift, oops, not second shift, I want to go to stat, calculate one variable stat on list 2, enter, and so I get that the sum is 500. There were 500 instances of somebody walking into a Costco and figuring out how many people were in the shortest line. So now I want to go back to my list, edit, and now for list 3, I'm going to find the probabilities. So I'm going to make list 2 divided by 500. And those are my probabilities. I took each one of the values in list 2 and divided them by 500, the total frequency, and I get the probabilities. So now all I have to do is copy those onto my table, and I'll get the desired results. So 0, 1, 2, 3, 4, 5, 6, 7, 8. The answer's right here, 0.026, 0.058, they belong here. Okay, so let me do that. Okay, next let's use our calculator to create a probability histogram. Notice that the values are in list 1 and list 3. So let's go to stat plot, turn it on. We want to turn it on. We want to select this, histograms, which is this option. And now list 1 is the possible values. And then the frequency is in list 3. Okay, so now let's go to window, and we got to choose the appropriate value. So we're going to go from 0 up through and including 8, which means that there are 9 values when we include 0. So let's put from 0 to 9. We'll play around with that afterwards, see if it works. We want the x scale to be 1s, yes, multiples of 1. We want the y's to be probabilities, and they're going to range from 0 up through maybe let's try 0.5 and see what that looks like. And the scale of 0.1, so it looks good. So let's graph that and see what it looks like. Okay, something similar to that. Okay, so this is a value of 0, a value of 1, 2, 3, 4, 5, 6, 7, and 8. And then the height represents its probability, so in multiples of 0.1, so 10%. So we have 10, 20, 30, 40, 50. Okay, so here's 10. So this is much smaller than that. Like this was our 2 point something. Okay, so this is a nice guide for us to be able to do a rough picture of this. So Okay, so that's a rough graph there. Not perfect, but pretty close. So notice that they're all rectangles. They're touching. The center of each rectangle describes which value that rectangle is representing. So 0, 1, 2, 3. It is not proper to put 0 over here in the corner. 0 is a valid possible answer, so it belongs in the center of this box, and there are 8 of them. And at the top of each box, each rectangle, you're supposed to write down the probability that it represents. So for example, 17% is the likelihood that exactly 2 is our answer. Okay, so now we can move on to part B. Part B says to use your calculator to compute the mean of the random variable x. No work needs to be shown. Okay, so let's use our calculator to do that. Remember that we already have all the values of list 1, list 2, containing the number of customers at Costco, the frequency, and then the probability. So to find the mean, we need to go over to list 4, and we need to multiply all the values from list 1 times all the values from list 3. So each value of x times its probability. That'll populate that result there. And now what we need to do is add those values. So we need to do a one variable statistic on L4. And there's the sum. And the sum of all those values is 4.842. So that's the answer that belongs right in here. Okay, so write a complete sentence to interpret your results of part B. Okay, so there are several good answers to this. I'll take something like the average number of people waiting in a randomly selected Costco's shortest line is 4.842 people, or approximately 5. Part D. If you walk into a randomly selected Costco at a randomly selected time, what is the probability that at least 6 people will be standing in the shortest line? The probability that at least 6 people are standing in the shortest line is equal to the probability that there are 6 or 7 or 8 according to our distribution table. The probability that x is at least 6 is going to be equal to that x is greater than or equal to 6, which is equal to the probability that x is in fact equal to 6 plus the probability that x is in fact equal to exactly 7 plus the probability that x is in fact equal to exactly 8. So we can just take the values from our table above, and we'll get that this is equal to the sum of 0.228 plus 0.138 plus 0.156, and the whole thing adds up to 0.522. Okay, part E. If you walk into a randomly selected Costco at a randomly selected time, what is the probability that at most 10 people will be standing in the shortest line? Justify your answer. Okay, this one's a little tricky because there's only x only takes the values between 0 and 8. So how can this be asking us about 10? So it was a little tricky, but okay, consider this. The probability x is less than or equal to 10 is equal to this giant sum of the probability that x equals to 0 plus the probability that x equals to 1 plus the probability that x equals to 2. Okay, dot, 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 dot here. So we keep going for all of them. And then, of course, we keep going until we get to the plus the probability that x equals 8 plus the probability x equals 9 plus the probability that x equals to 10. Okay. I guess I could have just put all those in one. Okay, well, since the random variable can never be equal to 9 or 10, how do we describe that something can never happen? We say it's got a probability of 0. So this got a probability of 0. This has a probability of 0. Okay, and now all of these guys here, well, they're every possible value of x. So all of them add up to 1. So, therefore, the probability that x is less than or equal to 10 is actually equal to the probability that x is less than or equal to 8, which is just equal to 1. Right? 100%. Okay, moving on. Okay, suppose that the Dunlop tire manufactures a tire with a lifetime that approximately follows a normal distribution with a mean of 70,000 miles and a standard deviation of 4,400 miles. Okay, so let's look at our distribution. What proportion of tires will last at least 75,000 miles? Okay, so first of all, let's label this. It's a normal distribution. It's not standard normal though. And it's got a mean of 70,000 miles and a standard deviation of 4,400 miles. Okay, and we want to know what is the value, what is the proportion of tires that will last 75,000 miles or more. So somewhere over here is going to be 75,000 miles. And we want to know what is that proportion, what is that area. Let's say that the 75,000 starts there. 75,000 or more. So I want to shade in this area. Okay, the probability that x is greater than 75,000 normal CDF of 75,000 up through positive infinity, here represented by a bunch of 9s, with a mean of 70,000 and a standard deviation of 4,400. So we punch that into our calculator and we're going to get approximately 1279. Okay, moving on to the second one. What is the probability that a randomly selected Dunlop tire lasts between 65,000 and 80,000? Okay, so we got 65,000, and we're also going to have 80,000. Let me put those on my graph. This still has a mean of 70,000 and a standard deviation of 4,400. And so we're looking for the area that's approximately between these two values. So that area right in there. Okay, so probability statement is going to be that the probability that probability is going to be equal to Okay, so let's go to our calculator and figure out what that is. So I'm getting approximately 8606. Okay, so the answer here is going to be equals approximately 0.8606, about an 86.06% chance that one randomly selected tire will last between 65,000 and 80,000 miles. Okay, moving on. Okay, suppose that Dunlop guarantees the replacement of any tire that lasts for less than 60,000 miles. What proportion of tires will last 60,000 miles or less? So somewhere over here is 60,000. This is still the same distribution with a center or a mean of 70,000 and a standard deviation of 4,400. Okay, so let's put an approximate line here. And so we are looking for values that are inside this little tail. Okay, so we want the values that are in that little tail, but not this. Okay, so this is also a standard, it's a normal distribution. So let's label it. It's normal. Okay, and so now let's write down our probability statement. Okay, so now let's go to our calculator. Normal CDF between negative infinity, so negative with a bunch of nines in there, comma 60,000, comma 70,000, comma 4,400. And we get a value of 0.1152, approximately 0.01152. There's about a 1.152% chance that a randomly selected tire will last less than 60,000 miles. That's pretty good. Okay, so finally, last question. Suppose that Dunlop wants to replace no more than 3% of its tires. What mileage should the company advertise as its warranty? Okay, so looking at our distribution, we want something that traps the lowest 3%. Let's just draw it on here. Okay, so let's just assume that that's about 3%. Let's label this. This is a normal distribution. We still know that the mean of this is 70,000. And the standard deviation of this is 4,400. And this is what we're after. We don't know what this is. Let's call it capital X here. I want the X value that brings down or separates the lowest 3%. So let's label this as 3% of the data. So the probability statement we're going to need is that X is going to be equal to, and let's label our calculator function. It's going to be inv norm of 0.03, 3%, comma, with a standard with a mean of 70,000, 70, 1, 2, 3, comma, 4,400. Okay, so now we can go to our calculator and figure out what that is. Distribution, inverse norm. And remember, the calculator wants the area to the left which we know is 0.03, comma, with a mean of 70,000, 2, 3, comma, and a standard deviation of 4,400. Close parentheses, and we get 61,724. Okay, and so we can approximate that to the nearest mile up, 61,725. So if they set their warranty at 61,725 miles, they're guaranteed that no more than 3% of their tires manufactured will fall under the warranty and require replacement.